Hello everyone. In the previous lecture, we discussed about the cell model, and in the cell model we discussed the nucleons orbiting in their individual orbitals. So it is sort of a weak interaction among the nucleons, though the nuclear force is a strong force, but the nucleons in their individual orbitals do not interact with the other nucleons in other orbitals. And by solving the Schrodinger equation of a nucleon using the potential though it is non-central, we assume that it is a central potential offered by other nucleons to the particular nucleon. We get the energy states of the nucleons, and whereby you populate those levels to get the configuration of the nucleons in the nucleus. And the cell model could explain the magic number. So that will be the application of the cell model. What are the different applications? What were the limitations we discussed in terms of liquid drop model? We can now try to see how this cell model scheme explains those things. So the cell model explains the magic numbers. Just now we saw in the previous lecture. By introduction of the spin orbit coupling between the L and the S value, the coupling of L and S, we could regenerate the magic numbers. Essentially, because of the strong spin orbit coupling, the L plus half state is lowered and the L minus half is raised, and the gap between L plus half and L minus half increases as the L value increases. Now, the high value of suppression energy of protons and neutrons for magic number of magic nuclei mean those nuclei which have magic number of nucleons and protons. This can be explained by large energy gap above the closed cell. So when you want to, so that is like a tightly bound nucleons in the closed cell are tightly bound. To remove any individual nucleon from that tightly bound shell, it requires extra energy, and that is why the suppression energies are higher. If you have a neutron more than or a proton more than the magic number, then again it is easy to remove that particular neutron or proton from the nucleus having magic number of nucleons. The absorption cross section for such a nuclei which have magic number of protons and neutrons again is very high, very low, because again the large energy gap above the closed shell. The ground state, and now this is important. Now the cell model can explain the ground state spin and parity of the nuclei. In fact, the liquid drop model could not explain the spin and parity of nuclei in their ground state. Also, the liquid drop model could not explain the nuclear isomers by using in cell model. We can able to explain the existence of isomeric states. The nuclear isomers are nothing but excited states of nuclei which are having metastability, means having higher half-life. So they don't come down by gamma decay immediately. Normally, gamma decay will take place in picoseconds time, but the isomers will take about, maybe it could be milliseconds, seconds, or minutes, hours, and so on. In addition to these properties, there are other properties of nuclei, the magnetic dipole moment of the nuclei and the electric quadrupole nuclei also can be explained using the cell model, but I will not discuss these 2 points in this particular course. Okay. Now let us see how we can explain the magic numbers. Just now we discussed this, that the magic numbers arise whenever there is a large gap between, in fact this is called the cell. Essentially the concept of cell has come because that we have a cell, like after this 8 and 20, this 8 nucleon, there is a large gap. So this is one shell, let us say cell 1, second shell, third cell. like this. This is third shell, and then you have the fourth shell. So this is the shell, and so there is a gap between two shells. Another shell we have. So the different orbitals levels have bunched together, and in fact there is a, now you can see the nucleons can occupy the states. The energy of these orbitals are very close, and the result of that close energy between the different orbitals we will discuss subsequently in explaining the properties of nuclei, particularly the ground state spin and parity. So the concept of shell has come because after that closed configuration there is a large energy gap, and so the nucleus will try to attain that configuration. So if there is a neutron extra over this shell configuration, closed shell configuration, it will be easily able to give that nucleon from the to form the closed shell configuration, and that is what is the concept behind the shell model. So the spin orbit coupling we introduced to explain the magic numbers. The high suppression energy of the nuclei having magic number of protons or neutron can be explained by the large energy gap here. So this is a very compact nucleus, and similarly the low suppression energy for the nuclei one above the magic number, again because of the magic number configuration. Above the magic number, if there is one nucleon, it can be easily removed. So energy required to remove a nucleon over the magic number is much less. Again, suppose you have a nucleus having 82 protons, then it has got a low neutron absorption cross section, because it would not like to take a neutron to become a one nucleon more than the magic number of. So this is how properties of the particularly with regard to the magic number can be explained. Now let us see how can explain the ground state spin and parity of nuclei. The bulk of this lecture we will spend more on this one. So when we say, so we will construct the cell model states for nuclei using the filling of the nucleons in the cell model states, and we will use that parity. So parity, what is parity? Is nothing but the -1 to the power L. That is the L state. So S, P, D, F, they have their parity, because essentially parity is the symmetry of a function. For example, if you take x to -x and this function changes sign, we say it is an odd parity. And if by changing x from x to -x, there is no change in the sign of the function, we say it is even parity. Like cos theta is a even function, sin theta is an odd function. Similarly, any function, any orbital, s orbital, d orbital, g orbital, L values are even. So this has got even parity because the L values are even. So any L value 0, 2, 4 is even parity, and any L value to 1, 3, and 5 are called negative parity. So depending upon the L value, the orbital state populated by a nucleon, we can straightaway say what will be the parity of that nucleus. Now let us see what are the thumb rules for determining the spin and parity of the nuclei. So first is the even nuclei. It's very simple. Even nuclei, all the nucleons are paired up, and therefore this spin will be 0 and parity will be plus. So the ground state spins and of the even nuclei are always 0. So any nucleus which is even, you can straight away say the spin will be 0. When it comes to odd A nuclei, either the neutron will be odd or proton will be odd. So the spin of that nucleus, the ground state spin of the nucleus will be the spin of that, the J value of the last occupied orbit. So J of the I will be equal to J of the last occupied orbital, and we will see subsequently how to do that. There are odd nuclei. In the case of odd nuclei, there is a odd proton and there is a odd neutron, and so the odd proton and odd neutron coupled together to give you the spin of the nucleus, and it is little complicated. So there are rules which are called Nordheim's rules. By using Nordheim's rule, we will try to predict the ground state spin of ordered nuclei. So now let us see how to build the cell model states. I give you some examples like helium-4. Now helium-4 has got 2 protons and 2 neutrons. So you will say, so when I say pi, essentially I am being proton, and when I say neutron, nu is the neutron state. In the single particle, this cell model is also called single particle model. Single particle means you take individual nucleon in a potential and generate the label scheme. So sometimes cell models are also called single particle model. And for single particles, the states are like proton status pi and neutron states are nu. So what is the orbital occupied by the proton? We say pi as half and nu as half. So 2 neutrons are paired in the nu, this half, 2 protons are paired up in this. So I equal to 0 plus, very easy to construct. If you try to recollect the scheme, so I can see here that you have first this S orbital, so it will be S half. Then you have 1s, 1p, 1p will split into 1p 3 by 2, 1p half. Then you have 1d will split into 1d 5 by 2, 1d 3 by 2, and you will have 2s. It will be 2s half. And like that, you can build up the scheme. So for oxygen 16 again, oxygen 16, you will have, I think there is some mistake here, oxygen 16, so it is 8, it should be 0 plus order, even nucleus. Pi as half 2, 1p 3 by 2 and 1p half, or 8 nucleons you occupy. And again neutrons, nu 1 as half 2, 1p 3 by 2, 4 and 1p half. So it is actually 0, not 1, not half. So in fact any even nucleus you will have the I equal to 0. Let's come to the ordered nuclei now. So oxygen 17, 8 protons and 9 neutrons. So it is what you have to see is which is the orbital occupied by the 9th neutron. The odd neutron, that is the 9th one. And if you start filling from here, so you will see S half 2, P half. So for the protons, forget about protons. About the neutrons, so you will have 9 neutrons you populate, S half 2, 1p 3 by 2, 4, 1p half 2, and you are left with 1 neutron that will go to 1d 5 by 2. So the spin, the J value of the last occupied orbital will be the spin of that particular nucleus. So I equal to 5 by 2. Since it is a d orbital, it is 5 by 2 plus. So that is how we calculate the spin and parity of the ground state of a nucleus. For example, you have oxygen 15, n equal to 7 neutrons. So you will see again proton states we don't have to bother. As the neutron states, you have now S half 2, 1p 3 by 2, 4 and 1p half 1. So 1p half is the last occupied orbital by the odd neutron, and accordingly the spin is J is half and parity is P means minus. So this is how you can explain, you can derive the spin and parity of the ground state of a nucleus by building up the cell model scheme and finding out what is the J value of the last occupied orbit. Okay, so we discussed the even nuclei, ground state spin is 0. We discussed the odd A nuclei. Odd A nuclei ground state spin is the J value of the last occupied nucleon, last occupied orbital, and depending upon the orbital, the parity can be defined. And now let us see for ordered nuclei how we can calculate the ground state spin. So for ordered nuclei, we have an odd proton spin, Jp we will call, and we have an odd neutron spin, Jn. This Jp and Jn will couple together to give you the resultant spin of the nucleus. Now, in this case, there are some Nordheim's rules which apply to what we call as the Schmidt groups. Now, what is the Schmidt groups? Actually, what happened now? When if we, I have not, we are not discussing the magnetic dipole moment of the nuclei, but when you plot the magnetic dipole moment of the nuclei, having last occupied orbital either in J plus, L plus half or L minus half states, what was found that the magnetic dipole moments for these two groups of nuclei. What are the two groups? Means that whether the nucleus is the levels are the last occupied orbital is J plus L plus half or L minus half. They lie on two lines, and these two lines, that is L plus half, having magnetic dipole moment in one way, and the L minus half state magnetic dipole moment the other magnitude. So there is a gap between the two groups. They are quite different magnetic dipole moment depending upon the J value, and they are called the Schmidt groups. So a Schmidt group is actually the classification based on the magnitude of the magnetic dipole moment, whether it is L plus half or L minus half. So the same analogy will derive here. Nordheim said that if the odd neutron and odd proton, they belong to the different Schmidt groups. So when we say different Schmidt group, means one Schmidt group is L plus half, other Schmidt group is L minus half. That is what we mean by Schmidt groups. In fact, we can suffice to say if they belong to different value of L plus half or L minus half. So if the odd proton and odd neutron belong to different Schmidt groups, that means one of them is L plus half, other one is L minus half, and vice versa. So if Jp is L plus half and Jn is N minus half, then J, the spin of the nucleus is the magnitude of Jp minus Jn. Difference between the difference between the Jp and Jn absolute value, that will be the, because the spin is not negative sign, the spin is always positive sign. Integral number, the value it can be plus or half integral or integral, but it is plus. So Jp minus Jn will decide the spin of the nucleus. Just to give you an example, chlorine 38, chlorine atomic number 17, and you have 17 proton and 21 neutron. How you try to accommodate them? So let us see how 17 protons you can occupy. You will see that the last proton will go to D3/2 state. Now the 21st neutron will go to F7/2 state. So you can see here that D3/2 is L minus half and F7/2 is L plus half. Because D3/2 is L minus half and F7/2 is L plus half. So they belong to the proton and neutron occupy orbitals having different Schmidt groups. And so Jp will be 3/2, which is L minus half. Jn is 7/2, is L plus half. So the nuclear spin of this chlorine 38 will be difference between Jp and Jn, and that is 3/2 minus 7/2, or 7/2 minus 3/2. It is the mod of that. So that is equal to 2. And chlorine 38 ground state spin is indeed 2. So the Schmidt group, this Nordheim's rule very well explains the spin of the nucleus having a odd configuration. The second aspect is that if the odd proton and odd neutron belong to the same Schmidt group, so there is in fact, it is not that easy to predict the spin of this nuclei having odd proton, odd neutron in the same Schmidt group. But then we say that for such nuclei, the nuclear spin is more than Jp minus Jn. So it is not easy to just predict it will be what value, but it will be more than Jp minus J. So this is a very simple classification where then you have to see what value it is. For example, the aluminum 26. The aluminum 26 having 13 proton and 13 neutrons. So the 13th proton will occupy D5/2 and the 13th neutron will occupy d5 by 2 because same value of proton and neutron numbers. So Jp is 5 by 2, which is L plus half state. d5 by 2 is L plus half state. Jn is 5 by 2 L plus half state. So here is the case where both proton and neutron occupy the same Schmidt group, that is L plus half. For such a nucleus, I is more than Jp minus Jn, that is, it will be more than, now 5 by 2 minus 5 by 2, 0. It's more than 0. But experimentally, the value has to be found to be 5. So you can see here it has a range. It could be from 0 to 5. 5 by 2 plus 5 by 2 is 5. So it could be anywhere. And so that is the kind of guess it gives, that it is in that range. But you cannot exactly pinpoint what will be the value of the spin for such nuclei, where the odd proton and odd neutron belong to the same Schmidt. Okay, so now, in fact, the cell model, it is not completely successful in predicting the ground state. Already we have seen in the ordered nuclei. So there are a lot of cases where ordered nuclei, cell model cannot give exactly, it will give a range. Okay, it will be more than this or it will be equal to this, depending upon in which Schmidt group they occupy. But for the odd A nuclei, or even nuclei is very same, it is 0. Odd A nuclei, by and large, the cell model can explain the ground state spin and parity. But there are some discrepancies, and that discrepancies we'll discuss here. So discrepancies in the cell model prediction and the observed ground state spin and parity. There are two important phenomena which, in fact, will lead to these discrepancies. First is the pairing energy. Now, what happens, in odd nucleus, so there are cases in a particular shell where there are different orbitals and which are close by in energy. The energy gap is very small. So if the thumb rule is that if a odd proton is there and it happens to be occupying a high spin state, let us say G9 by 2, H11 by 2, then, and if there is a nearby low spin state which is filled up, then what happens? There is a transition that the paired nucleon will like to remain in the high spin state because there will be a gain in the pairing energy. So the pairing energy depends upon the J value. So as you discussed, no, the higher the L value, the gap between the two states, L plus half, L minus half, increasing. So if there is a one odd proton or odd neutron, it will be jumped to a low spin state, and so the pair will go to the high spin state, and that would lead to discrepancies in the cell model prediction. So whatever you predict based on this cell model, the spins are different from the prediction, and that I try to explain using this slide. So arsenic 75 atomic number is 33. So we have the last, you have 42 neutrons. So this 33rd proton, what is the spin state of 33rd proton? You can see here last proton state F5 by 2. F5 by 2 is the occupied state, and according to this one it should be I5 by 2 minus. But actually the observed value is 3 by 2 minus. So here I try to explain the F7 by 2 will be 28 protons. Then we have after that 2p3 by 2. So 4, 28 plus 4, 32, and plus the last one goes to F5 by 2. So according to cell model, the proton should occupy F5 by 2, and hence its spin should be 5 by 2 minus. But you see here, just before that, there is a P3 by 2 level, and that P3 by 2 level is so the instead of that 33rd proton occupying F5 by 2, the pair goes to F5 by 2, and the odd proton occupies the P3 by 2. So this is what happens, that the paired configuration is having higher energy if it is higher lower energy if it is in a high spin state. And so the F pi by 2 gets stabilized by a paired configuration, and the odd nucleon goes into the P3 by 2. Similarly, iodine 127, Z equal to 53. So 53rd proton, you can see the last proton state is G7 by 2, so it should be 7 by 2 plus. And so you can see here the cell model states the 50 proton configuration, 50 numbers here, and then we have the G7 by 2 and the D5 by 2. So the 53rd proton should have occupied 1G7 by 2 and spin state should have been 7 by 2 plus. But experimental value of this nucleus is 5 by 2 plus. And again, you can see here that the next state to this is D5 by 2, which is vacant. So it will try to remain the odd proton in the G7 by 2 is not preferred over that in the D5. So that is the explanation that the odd proton will prefer to remain in a lower J value compared to that in the higher J. Paired configuration will remain in the higher J value. So this is the one of the explanations for discrepancies in the cell model predictions over the experimentally observed values. So many cases you will find that this kind of changes will take place, and then another explanation, there are some cases where even this cannot explain, this pairing energy effect cannot explain the ground state spin parity, particularly in the case of mid-cell nuclei. So this mid-cell nuclei, what I mean by mid-cell nuclei, so when we have 50, 82, 126, these are cell somewhere here. So if around 100, if the proton number is 100 or neutron number is 100, then for those nuclei, the nucleus is deformed in their ground state. And for such nuclei, again, you will find, you can just to give an example to illustrate this point, erbium 169 has got n equal to 101. And so the 101st neutron, if you see the cell model state, it should occupy the 5 by 2 state, and accordingly its spin should be 5 by 2 minus. But actually the observed spin is 1 by 2 minus, and there is no half minus state. There is no s orbital or p orbital. It should be, actually you can see it should be corresponding to p half, but there is no p orbital p half in the vicinity of this f5 by 2. Therefore, it was becoming difficult to explain how you can get this kind of ground state spins. So one of the explanations is that the collective motion. Collective model means in the nucleus, so other than the cell model, there is one more model called collective model, which I am not able to discuss because of the paucity of time. The collective model considers that all the nucleons inside the nucleus undergo a collective motion. Like the molecules have vibrations and rotations, the nucleus also has its vibrational states and the rotational states. They are called the collective states of the nuclei. And so apart from liquid drop and cell model, there is one more model called collective model. And the collective model has been validated by observation of the spectra, the rotational spectra. Rotational spectra, the ground state, the low-lying states of a even nucleus, 0 plus, 2 plus, 4 plus, and the energy gaps, from the moment of inertia, rotational energy of a rotational of the nucleus, you can predict Bjj plus 1, where B is just close to by 2i. And so people have even found out the moment of inertia, there is a fixed ratio of the energy states for the nearby low-lying states of a collective nucleus. So for the collective motion, people have seen that if the nuclei follow that kind of a relationship, you can associate this with the rotational states of the nuclei. And so there is a mixing of collective states and the single particle states or cell model states, and that is one of the explanations for this observed spin values being quite different from cell model predictions. So this is another area where the discrepancies can be explained. And lastly, I will discuss the nuclear isomers. The nuclear isomers are the long-lived states of nuclei, excited states, and it happens whenever there is a large difference between the excited state and the ground state of the nucleus. So the gamma decay is not easy to happen, and so the gamma decay is hindered. So when the gamma decay is hindered, the nucleus, the excited state hasn't got a long lifetime. So you can see here cadmium 113, 48 protons and 65 neutron. That the ground excited state of this nucleus is 11 by 2 plus, and ground state is half plus. So the cell model states it can predict the ground state of this nuclei, and excited states are there. So there is a large delta spin change in the gamma decay, and therefore this isomeric state has a half-life of 14.1 years. Similarly, the technetium 99M, excited state half minus, ground state 9 by 2 plus. Because of the large change in the spin during the gamma decay, this decay is hindered, and therefore isomeric state has got a half-life of 6 hours. So again, you can see here the state Z is equal to 43 for technetium. The 9 by 2 is the state. So it is the 43rd proton will go to 9 by 2 state, and then there is a excited. So if you populate the excited state half plus, half minus, its decay to ground state is hindered, and so we can see this 99M technetium is the workhorse of nuclear medicine, used in single photon emission computed tomography. And this happens, the isomeric states are found just below the magic number. So you can see here the magic number is 82, and right from 70 to 82, or even right from 63. So these are all the tellurium isotopes have got isomeric states having these odd number of neutrons. So the 71st to 82nd neutron enter H11 by state, and nearby S half state is there. So again, the nucleus decides where to occupy. The pair will go to H11 by 2, and the odd nucleon will go to S half. So whenever there is a magic cell configuration, just below that, there is a large difference in the spin states of the levels, and the excited state and ground state have this difference, and therefore the gamma decay is hindered. So this is what explains the energy, the nuclear isomers. There are several nuclei having isomeric states. Many of them are having half-lives seconds to hours to even years also. So cell model can therefore explain the properties of nuclei, which are based on wherever there is a fluctuation in the property of the nucleus in terms of the mass or in the ground state spin and parities, binding energies, and so on. This can be explained by cell model very well. Thank you very much.